Let's look at another example of a related rate problem. A police car is driving up to an overpass at 60 miles per hour. When the police car is 0.3 miles east of the overpass, he sees a car that is 0.4 miles north of the overpass. The police determine with radar that the distance between them and the car is increasing at 30 miles per hour. What is the speed of the other car? Okay, so let's look at our strategies again for solving a related rate problem. And step number one is to make a sketch of the situation. So let's go ahead and do that. So in this particular example, we have some overpass. Okay, and it says here that a police car is 0.3 miles east of the overpass. So we will say this is east. So here's our police car. Alright. And we know that it is at 0.3 miles from the overpass. And it is going to the overpass, because it says it's driving up to the overpass, at 60 miles per hour. Okay, so there's our first piece of information. Now it says it sees a car that is 0.4 miles north of the overpass. Okay, so we have there's another car, and it is 0.4 miles north of it. And then it also knows that the distance between them is increasing at 30 miles per hour. Now at this moment, we actually don't know if this thing is going north or south. We just know it's this distance away. Now of course we could probably use, the math is going to tell us, but we could probably use some logic and say, well, if this is going this way, and this distance between them is increasing at 30 miles per hour, it must be driving this way. So I mean, we know that's what the result's going to be. But anyways, the math should show that when we're done. Okay, the next thing is we need to write an equation that has all the quantities in the problem. Now looking at this, it appears that, with an overpass, we'll assume that this is a right angle. And so when we look at the distance here and the distance there and then the distance between them, it looks like we have a right triangle. And considering we're looking at all the distances, it appears that this being x, this being y, and this being r, call this r, would be the best choice, and the Pythagorean theorem would be a good choice. So let's go ahead and write x squared plus y squared equals r squared. Okay, step 3 is we're going to implicitly differentiate the equation with respect to time. Okay, so the derivative of x squared is 2x dx dt plus 2y dy dt, and that equals 2r dr dt. Easy enough. Okay, so now we need to look at all of our values. So let's go ahead and go through a list here. So we have x. Now we know that x is 0.3 miles. Then we want dx dt. Okay, dx dt is the rate that x is changing. Well, considering x is the distance between the car and the overpass, the rate that it's changing is the speed that the car is going, the police car, and that's 60 miles an hour. And then the other thing is, well, we do have to take into account direction. And normally we make right positive and up positive. So in this case, because it's going 60 miles per hour to the left, it has to be a negative 60. So that negative is important in this case. Alright, then we have y. Let's see, y is this distance here, so that's 0.4. Then we have dy dt, and dy dt is the rate of change of this other car. And that's actually what we're trying to find, so that's our question. R. Well, R is the distance between, the current distance between the car, the police car, and the other car. And we don't know that. But we can use the Pythagorean theorem. X squared plus y squared equals r squared. And so we have 0.3 squared plus 0.4 squared equals r squared. Now you could go through the calculation, but I am noticing that this is a 3, 4, 5, so r has to be 0.5 miles. So I'm going to go ahead and put that down. 0.5 miles. And then we need dr dt. And in this case, it says the speed between them, the distance between them is increasing at 30 miles per hour. And so because it's increasing, it's a positive 30 miles per hour. Good. So now we can take our equation, 2x dx. I'll write that down again. We have 2x dx dt plus 2y dy dt equals 2r dr dt. And we can start substituting in our values. So we have 2 times 0.3. And then dx dt is a negative 60. We have 2 times y, which is 0.4. And then we have dy dt, that's what we're looking for. And then there is 2 times r, which is 0.5. And then dr dt is 30. Good. Okay, so let's go ahead and simplify. We have, let's see here, 2 times 0.3 is 0.6. So that would be a negative 36 plus 0.8 dy dt equals, well, 2 times 0.5 is 1, so 30. We add 36 to both sides, so we have 0.8 dy dt equals 66, and then we divide each side by 0.8, which I'm going to do that on a calculator. Yeah, 66 divided by 0.8 gives us 82.5. So it'd be dy dt equals 82.5 miles per hour. So there we go. Let's put a box that. So here's another good example of a related rate of change problem. One interesting thing about this problem that was different from the latter problem is that in this case everything within our equation was changing. So there was nothing we could cancel out. But because we were given enough information, we were able to substitute in all those values and get the fact that the car that's going north is going at 82.5 miles per hour.